A statistics major did not study for his final exam, so it was a true-false test. And he said, well, I can just flip a coin for the answers. The stats professor watched the student the entire 2 hours as he was flipping the coin, writing the answer, flipping the coin, writing the answer. At the end of the 2 hours, everyone else had left the final except for the one student. So the professor walks up to his desk and he goes, listen, I can see that you did not study for the statistics test. You didn't even open the exam. If you're just flipping a coin for your answer, what is taking you so long? The student replied bitterly, shh, I am checking my answers. So we're going to talk about probability and maybe some coin flipping. All right, so a random phenomena is a situation in which we know what outcomes could happen, but we don't know which particular outcome did or will happen. The probability of an event is its long run relative frequency. So again, random means we don't know the outcome. The probability is, on average, this percent we expect this thing to happen. Does that mean we can predict the next coin flip? No. But does it mean that on average I could predict, say, the percent of heads? Yes, it does. So for any random phenomena, each attempt or trial generates an outcome, and the outcome is what happens during the trial. So it's either heads or tails. So now let's take a minute and we'll look at this virtual spinner on Shodor. And they have these great interactive manipulatives. So I made this spinner, and you can see I've set it. So the Cedar Ridge purple takes up half. Then I couldn't do black, so I did white and silver, or gray, and I set those both to 25%. So based on these areas, you would predict that, let's say I did a total of 4 spins, I would have 2 purples, 1 white, and 1 gray, right? So that's what I would predict. And on one spin, I would get a 50-50 shot of getting purple. So let's see what happens when I went ahead and played with this spinner. So here we go. Purple, that's fine. Let's do it again. Purple, wait a second, I'm at 100%. The next one can't be purple, but it is. Well, not the next one, we won't have another purple. Got another purple. The spinner must be broken, don't you think? Let's try again. Okay, we got another purple. We got 100%. And another purple. 6 purples in a row. Wow. Finally, we got a white. Okay, it'll settle down now. Wait, we got another purple. And then a purple. I thought we were going to get a gray on that one. And a gray finally. So the thing is, this is not behaving very well. Why is that? We've only been doing 1 spin at a time. Now when we start adding more spins, you can see that the percentages are getting much closer to the predicted. Let me add 1,000 spins. And in the long term, yes, I got purple 50% of the time, and the white and gray each about 25% of the time. So it behaved. So the point is, when you're looking at individual events, probability is great, but it's not going to tell you for sure what's going to happen. It will give you a very good rough idea of what will happen in the long term. So what did we learn from this spinner experiment? Well, the law of large numbers says that the long run, like many tries, relative frequency, is going to get closer and closer to the true relative frequency, or in other words, it gets closer to the theoretical probability. On average, you're going to expect to get heads half the time. So, can you predict what the next flip of a coin is? No. But can you predict the percentage of heads over many flips? Yes, the overall percent of heads should settle down to about 50%. Now, there is a common misunderstanding of the law of large numbers. It's like, oh man, you're due. For example, if I had made no baskets, right? I'm doing free throws, and I missed 10 in a row. People say, oh, she's got to make the next one because she's missed 10. That would be a fallacy, all right? It is not true that the whatever device you're using is going to remember what happened before it. So the past does not play into the future when events are independent. So, for example, when flipping a fair coin, if I had heads come up on the first 10 flips, what's the probability that tails will come up on the next flip? Well, if you believe the wrong thing, you're like, oh, you're due for tails, you might predict closer to 100%, but the coin doesn't remember what you flipped. All it knows is that half the time it tends to flip heads and the other half tails. So it stays the same. It's still 50%. Now, what values can probabilities have? Well, the lowest value for a probability is 0. So the probability has to be greater than or equal to 0. What does 0 mean? Well, it means that something's impossible. It will not happen. Then the maximum probability you can have is 1 or 100%, which means for sure it's going to happen. Like, will you have a test after this probability unit? Probability is 1 or 100%. Now, again, so for any event A, the probability of A, that's how we write it, capital P with little parentheses, and then the outcome we're looking for is in the parentheses. It's going to be between 0 and 1. And all the probabilities, when I add them up together, have to add up to 1, all right? So if I said S to represent the sample space and I added all those probabilities, I would get 1. But that does not mean that the probability for each outcome would have to be the same. And for example, let's go ahead and look at the table of the sum of 2 die. So you can see the probability of 5 is not the same as the probability of 2. So how do we figure out the probability? We just take all the outcomes that are going to give us 5 out of all the possible outcomes. So we have 4 over 36, which is 1 over 9. And I can change that to decimal, 0.101 or 10.1%. How about a 6 or a 7? We'll just look at all the outcomes for 6 or 7. I can count them up together, or I can sum them individually. There are 5 6s, 6 7s. I can add their probabilities, and I get 0.306 or 30.6%. How about a number greater than 4? Now remember, 4 doesn't count as greater than 4, so I have to start with 5 and higher, which would be this group right here. Of these, there are 30 or over 36, or some of you might have said, hey, it's easier to count these 6 and take them away from the 30, which is what we did here. And we get 83.3% is the probability of rolling a 4 or greater than a 4. How about greater than or equal to 4? Well, then I add 4 into the group. And you say, oh, it's easier to count these guys. And so you can say either count up what's in the yellow, 33 over 36, or take the pink away from 1, and you get a probability of 91.7%. Now, another type of probability problem is like time. And the way we want to do it is there's this traffic signal across at A.W. Grimes at Gaddis School, very busy traffic signal. And someone checks a timing sequence and they say, oh, it's 20 seconds green, 62 seconds red, and 3 seconds yellow. What is the probability that the light will be red when you get to the intersection? All right. So basically, how many seconds will it be red? 62 out of how many total seconds in the sequence? Out of 85. And when I divide those, I get 0.729 or 72.9%. Now, let's say we talk about the complement rule, because I've kind of been using it already. And what does complement mean? Well, if I had amazing earrings on and you're like, Mrs. Overman, those earrings really complement your blouse or your face or whatever. It doesn't mean the earrings are talking to my face or to my blouse saying, hey, you look great. No, what it means is it completes it. It goes with it. So the set of outcomes that are not in A are the set that completes the whole sample space, and that's called the complement. And it's denoted by this, A with a little c. You can also have an A with an apostrophe. All right. The probability of a complement is 1 minus the probability of the thing. So for example, let's say the probability of rain tomorrow is 20%. All right. The complement would be not rain, because it's either going to rain or it's going to not rain. If the probability of rain is 20%, then the probability of not rain is 80% because together they make 100%. So the formula is the probability of the complement is just 1 minus the probability of the event. So we'll revisit those die rolls again. What is the probability of not getting a sum of 5? Well, the opposite of 5 is going to, so in other words, probability of the opposite of getting a 5 is 1 minus the probability of getting a 5. Well, there are 4 5s, so 4 out of 36 is 1 over 9. So I could say, oh, 1 minus 1 over 9 is 88.9 or 0.889 or 88.9%. How about not getting a 6 or 7? Well, I can take 1 minus the probability for the 6 or 7, which we calculated last time, and I get 1 minus 11 over 36, which is 25 out of 36, or 69.4%. Probability of getting a sum not greater than 4, which, by the way, this is how you could write it mathematically. So greater than 4, we figured out, was 30 over 36, and the complement is 16.7%. And there's the not greater than 4. What's the probability of getting a sum not greater than or equal to 4? So this is the original. So the complement is just these three right here. So 1 minus 33 out of 36, or just 3 out of 36, 1 out of 12, or 8.3%. Finally, let's look at this example where we have the timing again. And this time, instead of the probability of a red light, I want the probability of not getting a red light. Well, it's pretty much the same work I had before, except it's going to be 1 minus that probability. And remember, we calculated that was 0.729 last time, so I could have just skipped this piece and said 1 minus 0.729. And that should say 0.271, sorry, 0.271 right there, or 27.1%.